coal, a leading source of carbon emissions. Professor Graham Morrison's research has brought him to one of Australia's most important areas for coal-fired power stations.
Liddell Power Station is located in the upper Hunter Valley, which is about 200 kilometres north of Sydney, an area of major coal mining and a substantial collection of power stations.
Built in 1970 with 2,000 megawatts capacity, Liddell is the third largest power station in New South Wales. It burns coal to produce steam, driving turbines and generators to create electricity for 1.3 million homes. Whilst coal currently provides the fuel for 85% of Australia's electricity, this station may play a unique role in a big change. By connecting solar heat to help produce steam for the coal-fired power station. This solar thermal technology was pioneered by Dr. David Mills and Professor Graham Morrison in Australia. It is seen as a genuine alternative to coal and nuclear power.
It's taken about 15 years to get to this stage. About 10 years of development, design, raising money, trial projects that didn't work, and finally a full-scale project that's about to be put live onto the power station. It's taken a long time, but there's a real turnaround of interest in this type of technology now.
The scientists always intended to create standalone solar power stations, but having access to Liddell meant they could test their system within the facilities of an existing power station. Being able to prove the concept has created worldwide interest in their technology, and they are now building standalone solar power stations in the United States.
It's certainly world first in terms of direct connection to a power station. It's the first large-scale demonstration of direct boiling technology. That is, we produce steam directly in this solar collector. We produce steam at 275 degrees C, 50 bar. And that's the type of steam, temperature and power needed to operate turbines.
The technology works by capturing solar energy with reflective mirrors.
The tracking of the mirrors is controlled by a computer program that knows where the sun is at any moment in the sky, where the receiver is, and positions the mirror to be midway between the line from the sun and the line to the receiver. So there's a computer program that is positioning the mirrors throughout the day to keep the focal point onto the receiver.
The mirrors reflect solar energy onto the receivers positioned overhead. The receiver is made up of pipes filled with pressurised water.
These tubes are feeding very high pressure water into the receiver, 50 atmospheres, 50 bar pressure. The water, when it reaches the receiver, absorbs solar radiation and is converted to steam. By the time it gets 300 metres down the other end of the array, it's steam that can be fed directly to the power station.
Our technology is effectively just changing the boiler in such a system. Instead of using a nuclear boiler, we use a solar boiler. The solar boiler is very different in shape. It's maybe a square mile or 2 square miles or 10 square miles in size, but it's still just a boiler. And when you do that, you find that all of the other technology to make these things work is already there. It's all of the power station systems, people understand it in the utilities.
Part of the reason for making the film was to demystify some of the technologies, to explain how they work, to show people physically what they look like and how they operate. Quite often when we hear the term solar, people think of solar photovoltaics only, and the panels and the modules on our roofs. A lot of people don't know that such a technology as solar thermal exists, and this is a major technology that Professor Graham Morrison, who's here today, has been working on for some time. You'll see him in the film, and it's a great opportunity to talk to him about it. It's regarded as one of the large, really viable alternatives to coal and nuclear, and so I think it's really important that people know about these other alternatives.
I don't think we're going to run out of silicon. Silicon's a pretty common material. It's very expensive to get out of the ground into the form we want it, but it's using it smartly is what we have to do now. So the concept of thin films, that just every window you put in will have electric output, despite being standard. We'll see.
Perhaps a related question is the energy that has to go in to manufacture the systems. And here I think we can say that renewable energy has great advantages over some of the conventional systems because, well, with photovoltaics, as Graham says, going to thin films and some of the other developments like sliver cells, the amount of energy inputs to manufacture the cells becomes much smaller. So instead of taking several years of operation to generate the energy to build themselves, that will come down to under 1 year. With wind turbines, they can generate the energy required to build themselves within 3 to 7 months of operation, and then they'll operate for another 20 years or more. The main problem is that we don't have any hot rock technology generating on a large scale yet, but we probably will have at least the first small generation later this year in South Australia. What are the problems? Yes, it's remote, but modern high voltage DC transmission lines can transmit long distances with very low losses. They're not entirely cheap, but look, that needs to be done anyway. We need to upgrade our transmission system in Australia anyway, not just for hot rocks, but for wind power also. Most of Australia's wind power is actually in South Australia, but there's too much wind power potential in South Australia to be used within South Australia. And yet South Australia has only got very weak transmission links to Victoria and New South Wales through to the national electricity market, which is the main grid system. So we need to upgrade those links. One is called Murray Link, near Mildura, and the other one around the south coast, Hayward Link. And we could combine upgrading those links with building a transmission link from the geothermal region as well to integrate in with that system. So that's part of what we have to do in terms of the new infrastructure to facilitate renewable energy. Bioenergy too, which uses, for example, residues of sugarcane and wheat and plantation forests. That requires a somewhat more distributed grid system to feed the power in from a lot of small bioenergy power stations scattered around in rural areas, and that is another potential. And right now there are plans to spend, goodness knows, $20 billion upgrading the grid in Australia, but they're not taking into account the potential for renewable energy and the changes in the grid that would be needed to optimise our renewable energy inputs.
But this is the same problem with all these technologies. I'm involved in the solar thermal area, and one of the things that we've just gone through is looking for the best site. Well, the best site is the sunniest climate, but if that's too far away, problem. And so the sites are picked by looking where are the current grid lines. And fortunately, New South Wales is a very big grid line between Queensland and New South Wales, which goes through Moree, and Moree happens to be a good solar site as well. So you're right, you've got to put these plants as close as possible to where there's existing infrastructure, where there are railway lines that bring equipment, where you aren't too far from existing grid lines you can tap into. But ultimately, that's just what will happen in the first stage. Ultimately, we've got to make the jump and say, yeah, the best site is geothermal in South Australia, or the best solar site is somewhere way out west in Queensland, where there's almost no one there, and we've just got to put our power lines out there, because that's where we can make electricity. But there's no answer to that, because they're all going to be there, because we're going to need all of them. So it's not just one of these that's going to pick up and be the dominant one. There are various reasons in different countries, different energy requirements. They're all going to be needed for the future.
And actually, I would say in addition to that, that one of the very refreshing things that I found in the experience of making the film, in talking to all of the people in these renewable energy areas, this sense of cooperation, the sense of wanting to cooperate with each other, work together. To me, it's also the hallmark of